All right, EEE 145, Chapter 1, Part 2, Introduction and General Philosophies. So if you remember last time, we left off in talking about relays. So we're going to go more in depth in it today. So here, relays are in two different sections, or two different categories. You have microprocessor based, and then you have old mechanical based. Okay, some people might call it electromechanical. So it's basically, do you have a mechanical computers with spring rates, gears, and solenoids to do your logic, or do you just literally have CPU, memory, and hard drive and converters to do all the logic for you, right? Both are still in use. We're going more toward microprocessor because they're more reliable and they could do more things and have smaller form factor, right? So for example, if look at this image down here, you got 3 cabinets. All those little black boxes are mechanical relays, and all those blue boxes, those are all actual microprocessor based relays. I would not be shocked to say if this one microprocessor based relays can do almost half this entire cabinet's worth of relaying. Okay, that's why we only have like 1 or 2 or 3 per, but then you have several panels worth of mechanical relays. Okay. So what are some typical manufacturers of these type of relays you're going to see? SEL, Schweitzer Engineering Lab is probably the biggest one. They're the blue relays you'll see everywhere, right? General Electric has their own set of relays. Siemens Electric has their own type of. Schneider has their own type of relays. And the other big one is ABB. Okay. ABB used to be Westinghouse until they got bought out. Oops, I misspelled Westinghouse. Okay. Westinghouse. There's a few smaller manufacturers, but these are the big ones. I'm going to put a star next to SEL right here because the industry is pretty much going to SEL relays. The others can't really compete. So if you ever go to utility, don't be surprised if you see blue boxes everywhere. That's kind of the industry standard we're pushing to. Okay. Other devices you'll see, let's zoom out, is circuit breaker. So we talked about the relay itself. One thing I like to say is in the order of operations, you got your instrumentation transformers. Okay. See, they call current transformers and potential transformers. These are your eyes of the system, right? This feeds information to the relay. We talked about this on previous class. The relay itself, this is the brains of the operations because they make the decisions, but they cannot make a decision without knowing what's in the system. So they need the eyes, right? And after the relay makes a decision, the decision is then sent to the circuit breaker. And the circuit breaker is the muscle of the system, right? So the action of disconnecting the actual circuit and disconnecting the fault is done by the circuit breaker itself because the relay is not powerful enough to disconnect these the fault current. So these are what circuit breakers look like. There's 2 types. We have a live tank circuit breaker, live tank CB. And just to give you an idea, here's the wires coming in one side, here's the wires coming in another side, and there's these contacts like so, okay? And these contacts will push in and out, and that's your switching mechanism. They'll go in to be connected, and then they'll come back out to get disconnected. And it's typically spring-loaded or some type of mechanical force that'll push them in and out, okay? So in the end of the day, I mean, it's just a switch that opens. Okay. They're called a live tank because you have live voltage attached to it. Meaning, don't go and touch the switch at the top. You can see us on a very large tower, very high up in the air. right? So you should stay very, very far away from the switch itself. You could go down here at the bottom, right here, and you look at the panel, but don't climb all the way up there to the actual circuit breaker. The other type of circuit breaker you see is called a dead tank circuit breaker. They call it dead tank because it's more towards the ground. So you have your bushings. So you have your wire coming in through here, and then a contact is actually right here. Now, you can see you have these bushings right here. These are all insulators. They're insulating you from the high voltage. So the voltage here is actually 0 volts. Okay. So meaning it is there's no voltage. Oops. No voltage around the circuit breaker. Meaning you can theoretically jump on this. You won't kill yourself. Obviously, it's not recommended for safety reasons, but that's what a dead tank circuit breaker means. You could attach it to the floor. It's not going to blow up the system because there's no live voltage on the actual casing itself. Okay, versus the live tank on the left-hand side where you never want to touch that because it's live voltage. Okay, now there's circuit breakers have different methods of interrupting the fault. So no matter what, they have some type of switching mechanism that either opens or closes, right? So it's literally spring loaded and these things will slide in and out. When they make contact, current will flow. So the current will flow this way and it'll come out. Now, whenever it's operating, so let's call this one to where it's actually operating. So this is a closed position. So you can see they're physically touching. This is an open position. So in this case here, this will be 0 amps. Okay. Over here, when it's closed, the current will go straight through. So this could be like, let's say 500 amps or so, flowing straight through. Okay. Now, the problem with opening these circuit breakers quickly, you might have some arcing involved. So whenever you try to open up a circuit breaker, you might still have some current flowing through and it'll arc into the air. So we need to get rid of the arc. So we need some type of arc extinguish. All right. Typically, to do this, we can blow SF6 gas. Kind of like, think of it, you have an arc and then you could blow some powder into it, kind of like a fire extinguisher. It's called SF6 gas. That will take out the arc. Another thing is it could be oil filled. So oil by nature is dielectric, meaning it won't conduct. So when you open it up, oil will rush in and then it'll extinguish the arc. Another one is called vacuum filled, meaning you create an absolute vacuum inside a circuit breaker and electricity cannot arc through a vacuum because there's no electrons there for it to move. Okay, so that's a different way you should extinguish arc. Okay. Whenever you're buying a circuit breaker from a manufacturer, there's a couple of things you need to figure out. So let's kind of draw the actual circuit breaker itself. So typically they're squares like this. These just, so I said square means circuit breaker, so we're going to go with it. Okay, there's 2 things, major things that you need to figure out. One is your fault current or your interrupting current. How much current can this interrupt? Typically, let's say 20 kiloamps, right? That's one rating. How much it can interrupt. So if you have a very, very big fault, that's 20,000 kiloamps, you have to make sure you get a circuit breaker that can handle it. Because if you undersize it and so let's say we have 50 kiloamps worth of fault and you buy a 20 kiloamp breaker, when you try to open it, it's not going to actually open the circuit. 50 kiloamps will keep flowing through. So we need to make sure that we can handle that fault current. Okay. Another one is your load current. So remember, circuit breakers still have to have load current flowing through. This could be maybe like 2,000 amps. Okay, this is normal conditions. So a circuit breaker needs to be able to handle day-to-day operations of, let's say, 2,000 amps. But then once in a blue moon, when you have a fault, it needs to be able to handle that 20,000 kiloamps. And as an engineer, you're going to design and choose which of these, do I need a 2,000 amps, 1,500 amps for low current? Also, do I need a 10,000, 20,000, 30,000 kiloamp fault current? And the manufacturer has a chart, you could just choose which one. Obviously, the bigger the number, the more expensive it's going to be, right? So that's also a very big consideration, is how expensive you want circuit breakers to be. Okay, so that's probably just a real quick gist of circuit breakers and relays that kind of operate hand in hand. All right. The next thing we're going to talk about relays is ANSI, standardized device numbers. So people get tired of saying long-winded names like overcurrent differential, undercurrent differential, over voltage, under voltage, overcurrent, time overcurrent, instantaneous, all these. It's hard to keep track of what's what. So just like any organization, to make it easy, we could put numbers to it. Okay, so relays functions have a number designation. And ANSI and IEEE are not corporations, but groups in the United States that banded all electrical engineers together. And we kind of, as a group, said, let's standardize the playing field. A 21 relay means this for everybody in the United States. A 50N relay means this for everything in everybody in the United States. That way, when I say 21 relay, you know what a 21 relay is. They know what a 21 relay is. Everybody knows what a 21 relay is. Okay. Here is a PDF to kind of give you an idea of, or a chart of what do they all mean. So one good exercise we can have today is, let's go ahead and take a 20-minute break. You should open up this PDF, look at it, and try to answer all these as much accurate as possible. Some of them are just going to be literally just read off the chart. Some of them you might need to kind of put two and two together. Okay, so try your best, come back within 20 minutes, and then we'll compare answers. Okay, so thank you for watching. See you guys in a second. All right, welcome back. So let's continue EEE 145, Chapter 1, Part 2. So previously I said that we'd take 20 minutes to go look at all these ANSI numbers to kind of get a feel for them. So let's go down one by one and say what they are. So 21 relay, remember that is a distance relay. And again, we'll talk about what each relay means later on in the course. A 50N device is, a 50 is a instantaneous, so we call it instantaneous overcurrent. Some people call it just OC relay. And N stands for neutral, so it's an instantaneous overcurrent relay for the neutral wire. Okay. What's the standard number for a lockout relay? I believe that's an 86 lockout relay. And so on your sheets of paper, if you ever see what an 86 with a circle, that's what a lockout relay is, right? So you have a wire coming in, wire coming out. Same thing for a distance relay. You might have a 21 relay, and you have wires coming in and out, okay? What's the standard number for a differential relay protecting a transformer? So differential relay is 87. Now, kind of a trick here, kind of like with the N, transformer is T, so we typically put a T next to the 87 to denote that, hey, this is specific for a transformer nearby, so 87T. Let's select colors real quick. 50-51 relay, this is kind of a combination relay, so we call it combo relay that has a instantaneous OC overcurrent and a time overcurrent as well, because 51 is a time overcurrent. Typically, these are built together in one device. Okay. What's a 27 relay? So let's look it up. 27 is under voltage. So if this power system gets below a desired a voltage we set, we're going to trip something offline or do something. Okay. Switch some colors. So 59 relay is going to be opposite of that, I believe. That's an over voltage relay. Right. And just kind of give you an idea, we could set an equation where if it's even like an if statement, we could program, if X is greater than, I don't know, 12 kV, or let's say 15 kilovolts, 15 kV. Okay. If our readed value is above 15 kV, then we'll trip circuit breaker and we'll open the switch. Okay, so that's kind of how an overvoltage relay will operate. And we could choose what this 15 kV or another value. It could be 30, 80, 150 kV, whatever we want. But this is kind of the logic the relay will look at for a overvoltage relay. Okay. Lastly, what is the ANSI standard number for a AC circuit breaker? That's a 52. Protecting a generator. Again, since we're protecting a generator, that's a very unique thing. We could put a G right here. So a 52G would be a generator breaker, right? Not everybody does a 52G. Some utilities do, some utilities don't. But I just want to point out, if you ever see like 52G, that'll probably denote a generator nearby, okay? So as you see, you get used to the power industry. These numbers will kind of come second nature to you, and they're all, you won't even need a chart anymore. I'll be honest, 80% of these numbers you'll never use because they have to list every single device you'll come across. But there's a good 20 of these that you'll see on a daily basis as a protection engineer. Okay, so I have a chart printed out in my office. I think everybody will eventually get to that point if you're going to be a protection engineer. So please get used to these numbers. All right, let's keep on going. So we kind of talked about devices, and so we gave the problem of the faults exist, that burns equipment down. We barely touched the devices like fuses, relays, circuit breakers, and how we could use those to create a protection system. But now let's start talking about the protective system itself, right? Before we even get anywhere, we need to understand, what do we want to do with the system? Why do we need it? Okay, so the faults exist. So what do we want to do for the power system? We want to protect the system. So we want to protect the power grid. So one thing is protect the grid. Another thing we need to do is protect the equipment, right? So if something goes bad, not only can we damage equipment, we can also bring the entire power grid down and have a national blackout, and that's really bad. So most important, protect the grid, and equally as important, protect equipment. Another one that's very important is protect the people, right? I'm not going to lie, as a power or a protection engineer, you're going to have to go into substations. You're going to have to go play around with things in the substation. There is a chance that you might get hurt. So the better the protective system there is, the less of the chance that you're going to get seriously injured on the job, right? So this is why protection is mandatory for anything in the United States. Okay. So we know the three basic principles: protect the grid, protect equipment, protect the people. No, money has nothing to do with this yet. Okay. This is way past cost. Okay? This is literally like for the good of society level things. All right. So to accomplish these three major goals, we have 5 criteria we have to adhere to and balance. And I say balance because some of these are oppose each other. So we kind of have to have a middle ground compromise. Okay, so let's go down each one. So reliability is the protection system that we designed operates correctly all the time. All the time. Okay. We cannot afford a protective system to fail whenever we need it the most, right? It's like you get in a car wreck and the airbags don't work and you kill yourself, right? We cannot afford that. So that's one of the utmost requirements is our system needs to work when called upon. Okay. Now, selectivity is to disconnect. Oops, misspelled disconnect. So disconnect the minimum equipment to clear a fault. Why do so we don't if a house in a neighborhood is damaged and we need to rebuild a house, do we bulldoze the entire neighborhood and rebuild all of them, or just that one house, right? You want to only take out just equipment that got damaged or the minimum amount that's problematic, not everything. Because if you take out everything, you might black out half the city. Okay, so disconnect the minimum equipment to clear the fault to maintain the maximum number of customers online. Okay, we don't want to, when an event happens, we want to drop the minimum amount of customers and have a minimum amount of disturbances in their life. Right? I don't like it when power goes out. You don't like it when power goes out. Nobody likes it. Okay. Next one is speed. Right? We want trip, or maybe not always trip, but act as fast as possible. And why? Because we want to have a minimum fault duration. Remember, we talked about earlier, the longer the fault is on the system, the more energy is built up as heat in the equipment, and there's a more chance that somebody will walk by and kill themselves. So let's get it off system as fast as possible to do the least amount of damage. Let's even put that, I want to emphasize more. The least amount of damage. Okay. Next is simplicity. This is that KISS, keep it simple, stupid, right? The minimum, let's use minimum amount of protection equipment. Now, this is very important. We want to use minimum protection equipment, but keep adequate protection. So don't go overboard and make a super complicated system that could clear everything faster than we need to, right? There's always that middle ground of, I want a simple system that still works good enough, not the best in the world, but good enough to make me feel safe, right? And then that goes it kind of dovetails into economics. If we keep the system simple with a minimum amount of equipment, we can maximize, or let's say minimize the cost, right? Because no one wants to spend money, not more than they need to. Minimize the cost for adequate. I kind of wrote that funky. Let me try that. Adequate protection. Okay, so those are the 5 big criterias, right? Economics, simplicity, speed, selectivity, and reliability. And depending on what you're going to design, you might have to sacrifice a little bit in one category to make another category better. And it's basically 5 bars we need to kind of balance out for the customer and what we're trying to accomplish at that specific scenario. Okay. Now, because we have five criteria we need to keep, and they're kind of a compromise of each other. This makes protection actually one of the hardest design systems in the world, because no two systems are the same, right? That's the biggest problem. We try to make utilities kind of build the same across the whole industry, but that never actually happens, because we might have a new design here and an old design over there, or somebody 50 years ago made a different decisions. So we have multiple designs, and then that it adds complexity. So think of it, let's write that down, let's capture that. Power systems are unique. Oh, another good reason why they're unique is because different cities are built different, have a different infrastructure. The way San Francisco's power grid is set up is vastly different from the way Sacramento's power grid is set up. So you can't protect both of them with the same plan. Okay, so power systems are unique. So we need unique plans, unique protection systems design. Okay, that's where you will come in. Now, when we start designing things, what's going to be the roadblocks and what are going to be the arguments with you, your boss, and your clients? Here's one of the arguments. Faults are rare. And they are. Some places might not even see a fault for 40 years, and somebody retires and says, well, this never happened. Well, you don't know. Tomorrow might. Lightning might strike, or a car might hit it, or something else, right? In 10 years, we might build a new Amazon warehouse there. Who knows, right? So faults are rare, so it's easy to skimp out on protection. That's what people always say. Everybody forgets about protection until something burns down, and then they come crying about, well, we should have done this, we should have done that, right? I'm going to say the possible damage of an unprotected system can be 100 times more than the cost of protection. Okay, so you got to ask yourself, would I pay $100,000 to install a protected system to save a $10 million substation? Right? Most people would probably say yes, but there are some people who say no, right? So ask yourself, is that 1% worth it? And again, different people have different ideas and philosophies. This is the hard part about protection. Some people say, absolutely, 1%, here's the money. Let's do a 5% build. We could do that. It'll be even better. I've had other clients and people say, I refuse to pay 1%, make it 0.5%. And I say, why 0.5%? He says, because you offered 1%, skimp out more and do 0.5%. And I say, if I go 0.5%, I can't even guarantee you the basics. So this conversation's over. Okay, so that's the economics of design. Money's a big deal. You're going to have to always argue with your boss or your client, is it worth it? Okay, and that's a big limitation, is money. Now, another one is personality factor. So I like to say protection is like an art. Is like an art project. We say that because when you design a system, unfortunately, there's no set rule on how to design system. Meaning I could design a system that works adequately. You could design a system that's different, that does the same thing. A third person can do it. And then as a client, he'll choose whichever one he feels the better or the cheapest. So there's always that personality factor involved. Another big personality is risk versus reward, right? Some engineers are risky, some engineers are more conservative. So how risk adverse are you? So this is a risk versus reward design aspect. Okay. Again, there's no right answer. There's no wrong answer. The only answer is whatever meets a minimum requirement and makes your customer happy. That's what matters, right? And just remember those minimum requirements on the previous page. Protect the system, protect equipment, protect the people. As long as those is covered, we can have multiple designs and let the client choose whoever they want, okay? Another big factor is location of circuit breakers and input devices. These are, you remember, this is your eyes and this is your muscle. Okay, where you put them in the substation or out on the field can impact the cost, right? Because it's easier to put it in some areas. It's harder to put it in another area if you have to dig a trench or you have to put a crane or maybe put some scaffolding to install it there. Okay, cost is another thing. Distance to the relay. Okay. If the circuit breaker or input devices are too far from the actual relay itself, you're gonna have to run a bunch of wires a couple 100 feet. That could really have an issue. Okay. Another thing is coordinating with other devices. So there's multiple circuit breakers, multiple input devices, multiple relays in a system. Like a substation could have 20 different relays. Devices. Ooh, I changed the color a little bit. Okay, so where you install it in your system has a big role. Okay. So again, this is unique to every system, every substation. You typically work with a customer, you work with your boss or substation engineer, and you guys come with a plan together to where the devices should be installed in the field. Okay. Another big factor that we need our protection system needs to figure out is the ability to distinguish faults from normal operations. Remember, faults are high currents, right? Versus load current, which is smaller. Okay. We need to design our system so we know what to do. Remember, fault currents, we want to trip the circuit breaker. We want to disconnect the system. Low current, we want to keep in service. So keep the circuit breaker closed. We need to somehow design our system to distinguish between these two. Otherwise, we're going to have a big problem. The last thing you want to do is for your protected devices to operate and disconnect everybody and have a false alarm whenever there was no problem to begin with. It's kind of like a fire drill where somebody hits a fire alarm and everybody has to evacuate the stadium. Boy, people are going to be mad. Same thing here. If we have a fault, if we don't have anything happen and then your protected device shuts off the hospital, shuts off the stadium, shuts off Sac State, you can get so many lawsuits slammed on you for that. So it's utmost that we need to distinguish between faults and regular conditions like low current. And these regular conditions can also be a hot summer day. So we'll say maybe, a hot summer day with everybody running AC. This could be a problem where we still need to make sure that we're massively loaded down, but we're not into this burned equipment down fault territory. So we need to make sure our relays don't operate. And there are plenty of times in history, especially California, where it's extremely hot. We have a heat wave and protected devices have operated in the past and knocked out all of Los Angeles. Okay, so we want to make sure we try to design a system that would never happen. okay? Now, talking about good things and bad things, we need to know what is a good performing system, what is a bad performing systems, and kind of, how can we gauge how can we gauge if we're doing good or bad, okay? So what are an example where a protection system works correctly, right? So number one, it detects a fault. So if there's a fault, it detects it. We need to make sure we know it's there and we can't miss the fault, because then we immediately fail. So first we need to detect the fault, and then number two, we need to make the correct decisions, right? And so the primary system, the primary protection system operates. Okay. And then number three, the fault itself, the faulted area is isolated. Okay. So as long as all three of these work, we're fine. Now note, I said primary right here. Now I'm going to put a star right here. We typically have a backup system exists. Okay, so backup protection did not operate. So if we're running everything optimally, our primary layer of protection would operate and not fail, and the backup protection did nothing. Okay, the backup system is there in case the primary fails for some reason. Okay. Now, what is this? What would be a example of incorrect operation? Well, let's do A, B, C. A misapplication of relay. Misapplication. I think I spelled application wrong. Misapplication of a relay. One misapplication relay is I meant to look at current, but then I installed a voltage relay by accident. So we're looking at the wrong quantity, so we're going to make the wrong decision. Okay. Number two is incorrect relay settings. So every relay you have to program. So the settings / programming is wrong. You forgot to put a semicolon somewhere. You forgot to put an AND gate or something, right? So your logic, something's messed up, right? Another one is your backup system, your backup protection operated. So because your backup system operated, by definition means your primary system either failed or they're not layered correctly. The backup protection should operate after the primary one. So if the backup one operated first before the primary one had a chance, that's also the system's not working correctly. Okay. Lastly, this is pretty rare, but we do have equipment failure, right? Relays can break once in 100 years, maybe, right? Circuit breakers can misoperate, but so we have to say, but this is rare. Majority of the time, it's the first three, A, B, and C. That's a telltale sign you did something wrong, but we can't rule out equipment failure as the last thing. Okay. Now, last thing I want to say about this part is some protection system can have an unknown factor involved. And what do you mean by that? Sometimes you could have something called race conditions. Okay, where multiple relays are trying to operate at the same time and one just happens to go faster than another, either by design or not. Right. Other things is natural disasters, like lightnings, can cause, we call this an abnormal condition, right? Or we call it transients on the system. Transient system conditions. Okay. So if a lightning strikes a power line, you might get a giant voltage for a split second. You might get more current than you should. The frequency might go all over the place, right? So sometimes there's some unknown things that happen and you can't quite explain why, right? We call these, quote, you hear it all the time in insurance, acts of God, right? Sometimes this stuff happens. I've known protection engineers that quit their job because of this, and then they can't figure it out or they can't design correctly. Look, sometimes things will happen. You don't know why. You have to accept it and move on, right? And roll with the punches. I mean, that's the best advice I could give you whenever these type of crazy things happen, and they'll happen a few times in your career. Okay, so that's pretty much the performance of protection system, right? Kind of, we could go talk about when we're applying relays, what's a way we could start applying it to where we're not overwhelmed too much. One of the big things we do is we create zones of protections. So they're small pockets of an area we protect. And we ignore anything outside. The zone. The pocket/zone. Okay, pocket, zone, they're the same words. Okay. It's just for simplicity's sake. I don't want to make a system that protects everything in the world, because then if one piece breaks, the whole thing goes down, right? Let's go ahead and modularize our zones and say, hey, let's just have one zone for one thing, another for another. So for example, here, we have one zone right here, right? And this zone is for the unit generator and transformer zone. So we have one zone that protects the generator and transformer. Okay. Note that dotted line, we put the transformer generator and nothing else. Another one we have is, look at this dotted line. We have a line zone. So this protects the line, the transmission line, right? So we have a line zone. What others can we have? Well, let's go down here. We have this group. This is called a bus zone. So this protects the bus. Okay, bus is a fancy way to say node, by the way. If you never heard, a bus equals a node in circuit analysis. Okay, that's all it is. Another thing we could do is a motor. So right here, we have a motor. Motors are big, expensive. We need to protect those. We could protect the motor. Protect the motor zone. So just to make design easier, instead of designing everything all at once, let's put it into bite-sized chunks and say, let's just design this zone first and design another zone. And then one by one, and they're nice and modular, so you can take one out, add one in, and you can modify them little by little instead of all at once, right? Just in general, project management, engineering design is better to design small little pockets and put them together than try to do everything all at once. Okay, so you're going to see zones of protections a lot in protection, and we're going to go through and show you the optimal way to set the zones. Okay. The very last thing I want to talk about is the big picture. We talked about individually how to design this, how to design that, little devices. Let's zoom out to all of California and all of the United States, and let's see what's the big picture of the protective system, not just our grid, not just our small little pocket in Sacramento. So, speaking of Sacramento, who are the utilities near Sacramento? You should know SMUD is what we use in Sacramento, and the surrounding area, which is right here. The surrounding area is PG&E. Okay, so if you live in the foothills, you have PG&E. Those are the two big areas. We have a small one called Roseville Electric as well, but they're most of the time they're so small they don't get printed on the map. Sad face. So those are the three utilities near Sacramento. You'll see, how can we work together to make sure our protection plan works across the entire system. We must talk with each other. And share our plan, okay? If I make a protection system, I need to tell my neighbor the plan so they could plan theirs as well, and we could mesh our plans together, okay? It's actually a rule that if Roseville Electric changes something in their protection system, they have to tell PG&E and they have to tell SMUD nearby, right? Otherwise, we can't plan effectively if you don't tell us your plan, okay? Now, who helps to make sure that utilities talk to each other and these plans are shared? It's called NERC. Okay, NERC is the North American Electric Reliability Council. Okay, so NERC is an entity. They're kind of like the police force that creates rules. We'll say, let's be nice. Let's say guidelines, right? We'll create guidelines on talking with each other. Think of them like the a therapist, where all utilities come together and they're there to help oversee the communication between the utilities. Okay. And then if a utility refuses to talk to each other, then they get in trouble. Okay. So NERC is a big thing, and all utilities have to be involved with them. And we have to talk to each other and tell each other the plans. Now, anytime we talk about NERC, we have to talk about regulatory agencies. So regulatory is another fancy name of saying rules. Regulatory, I spelled that already. Regulatory basically means rules and enforcement. That's all it means. Okay. So you can literally say, instead of regulatory agency, enforcement agency. So again, big regulatory agency for power industry is NERC. We call it NERC, not North American Reliability Council. Now, NERC is an agency to force everybody to work together. Now, under NERC, we have partnerships. Actually, technically, is a deputy. Okay. So just, if you don't know what deputy is, just make sure. A deputy is a person that gets kind of quote crowned by the sheriff to help them. So they're like assistants. Let's call them assistants. Okay. So we have several assistants in the United States to help NERC regulate, right? FRCC, MRO, NPCC, RF, CERC, SPP, Texas Reliability, and WEC. Now, look at the map. Which one do we fall under? Where's California? Right here. We are under WEC, Western Electric Coordinating Council. So for sure, if you work at a utility, you will have to answer to WEC. Okay. So just in an interview, if somebody ever asks you, what regional entity do you have? What regulatory agency we need to look after? Just say WEC. Okay. Now, what does WEC do? Like, WEC makes rules, but what are these rules called? Where are they? So I know I'm doing everything right. They're called reliability standards. Okay. So common protection standards are actually called reliability standards. Now, the one unique for protection is the PRC. Okay, so we have PRC standards that we have to adhere to as protection engineers. Okay, so again, we'll have PRC 27, 25. You could look at this link, and there's about 50 or 60 of these underneath the PRC that we need to adhere to based on the type of utility you have. Okay. So that's about all I have for today. So I thank you for showing up, and we'll see you guys next week. Take care.